Welcome all. So, today we will resume our 2 degree of freedom system analysis. Previously we looked into the 2 degree of freedom system. We started with our approximation of the single degree of freedom system. Then we subsequently looked into the examples of 2 degree of freedom system. We again talked about the approximation from changing a real life multiple degree of freedom system to a single degree of freedom system, and the same application which we can apply in order to make the same system and analyze this thing using a 2 degree of freedom system. After that we looked into an undamped system, okay, with no forcing function, and we evaluated the equation of the motion, and from the equation of the motion we calculated the natural frequency of the system. So, this we have done, and building upon this thing we will again continue our class today. Okay. So, let us start the class. So, picking up from the last time, okay, in the last time we had reached here where we were able to calculate the frequency of the system. Okay. So, we calculated the natural frequency of the system. So, omega 1 was the first natural frequency of the system and omega 2 was the natural frequency of the system. What it means is that we were dealing with this system, okay, having 2 degrees of freedom, okay, 2 degrees of freedom, okay, m1 mass m1 and mass m2 was there, okay, and the degrees of freedom x1 and x2 were there. So, omega 1, it means that the system is going to oscillate, okay, the first mass, okay, it will oscillate around its equilibrium position, okay, by what is degree of freedom with a frequency of omega 1, and this one is going to oscillate with a frequency of omega 2, okay, and the magnitude is given by this particular equation, okay, where each of the frequency is the function of all the stiffness values and the corresponding mass values. Okay. So, this is how we find out the solution for the frequencies. Okay. So, moving ahead. So, again we will come back to the equation. So, equation 3, okay, it can be again represented using this formulation, okay, and if we replace the ratio a to a1 over a number r, okay, so we are making a ratio a to a1 equals to r, okay. So, then we can rewrite this equation, okay, and from this equation we can again rewrite the corresponding equations, okay. So, what we are trying to do is that what was a1 and a2, okay, let us go back and look into what was a1 and a2. So, from the last class we remember that we formulated our responses in terms of harmonic functions, okay. Since there is no effect of the external forcing function, the external forcing function is 0. So, the system will behave in a harmonic fashion, and a1 and a2 are the amplitude of this harmonic functions, okay. And now we are depicting a2 over a1 as a ratio r, okay, which is nothing but the ratio of the two amplitudes, okay, and we are trying to find out what happens to the amplitudes, okay. So, first of all we find out the frequencies, and now we are looking into the amplitude, okay. So, this is r, okay. So, using this equation it means that k1 k2 omega square times 1, okay, and minus k2 times r, okay. So, k1 k2 minus omega square times 1 plus k2 times r. So, this is the first equation, and minus k2 times 1 and this number times r, this is my second equation, minus k2 times r, and second equation is this number, okay. So, using this we find out the amplitude ratios r1 and r2, okay, and we can put this back and we can get the solution of all the degrees of freedom, okay. We already have found out omega 1, omega 2, and we have found out the values of the amplitude ratios, okay. So, the generalized solution for 2 degree of the freedom system looks this way, okay. So, here what we have done is that we have used our older formulation, okay, x1 and x2 equals to a1 a2, okay. We find out the value of omega, we find out the value of a1 a2, and we put this thing back into the equations, and we got the generalized solution for x1 and x2. Okay. So, it means that this two equation depicts the motion of the two masses at the chosen degree of freedom. Okay. So, x1 gives the motion of the mass, okay, the harmonic motion of the mass with frequency omega 1 and omega 2. Okay. So, here one thing we need to understand one thing. Okay. In any given degrees of freedom, okay, in any given system, okay, the final total motion, okay, at any point, okay, will be a sum total of the contribution from all the individual modes. Okay. So, if we are looking at any chosen degree of freedom, okay, let us say we are looking at the center only. So, if you are looking at this point, okay, so y center. So, y center will be a function of the amplitude, okay, due to that an amplitude part times the shape function part, okay, and it will be summed over all the modes. Okay. It means that y will look something like this: q1 phi1, q2 phi2, q3 phi3, and so on and so forth. Okay. So, it will have a shape function contribution from all the modes, okay, and an amplitude mode corresponding to that particular mode. Okay. So, here also x1 and x2, okay, x1 will have a contribution from q1 phi1 plus q2 phi2. Okay. It means that it will have a contribution from the first degree of freedom and it will have a contribution from the second also. Okay. So, x1 will have a contribution from omega 1 and it will have contribution from the omega 2, okay, and so hence and so forth. Okay. So, in order to evaluate A1 and A2, we have to put the initial conditions, okay, and let us say we are assuming a case where all the k's are constant and all the m's are constant, okay, all k's are equal to k and all m's are equal to m, okay, and we are applying an initial condition, okay, and we are giving it an initial displacement, okay, at 1 degree of freedom. Okay. Velocity component we are keeping as 0 and we are assuming x1 and x2. Okay. So, let us see what is the behavior of this particular system. Okay. So, we have been given all k equals to k and all m equals to m, okay, from equation 4. Okay. The equation we derived earlier, the value of omega square equals to this much. So, the two natural frequencies are omega 1 equals to root over k over m and omega 2 equals to root over 3 k over m. Okay. Now, we need to determine the mode shape also. Okay. So, in order to determine the mode shape, what we need to do is that we need to put back all these things into this equation back, okay, or we need to put everything into back into this equation. Okay. So, if we do that, okay, what we will get is we have to do it one at a time. So, we will put the value of omega 1 first. Okay. So, if we put the value of omega 1, r1 equals to 1, okay, it means that the value of the amplitude corresponding to the first mode omega 1, okay, r1 equals to 1. Okay. So, r1 was nothing but the ratio of my amplitudes. Okay. So, this was my r and this was my equation for my r1 and r2. Okay. So, for omega 1 we have calculated our r1. Okay. So, for omega 1 r1 equals to 1, it means that the value of a2 over a1 equals to 1. Okay. It means that a2 equals to a1. Okay. So, now we will try to draw the mode shape. Okay. So, at degree of freedom 1, okay, the value is 1. Okay. So, at degree of freedom 2 it is also 1. Okay. So, it means that the mode shape will look something like this. It means that if this thing is moving 1 unit here, the other one is also going to 1 unit, similar 1 unit in the same direction. Okay. So, this is how we can represent the mode shape. Okay. It will become more evident and more clear once we are dealing with the beams and other system, but here it simply means that if we move the first mass 1 unit towards the right or 1 unit towards the left, correspondingly the other mass is going to move into the same fashion, okay, as far as the first frequency is concerned. Okay. So, when the system is acted by the first frequency, okay, the system is going to move like this. Okay. So, we can visualize this thing, okay, using our beam analogy. Okay. So, let us go back and look into the beam analogy. Okay. So, remember what we did in the beam analogy. In the beam analogy, what we did was we assumed this mode shape and we took this thing. Okay. So, here in the we took out two places. Okay. So, if the beam is moving in the first mode, okay, corresponding to a frequency of omega 1. Okay. So, if this thing moves 1 unit downwards, this will also move 1 unit downward. Okay. And this is how the shape of the beam will look like. Okay. Since there is no mass in between, okay, we are just joining this thing. Okay. So, this is being shown out here. Okay. So, in the first mode, okay, so first mode normally is looking like this. Okay. But since there is no mass in between, we are tracing out the value of the displacement of the two chosen degrees of freedom. So, first degree of freedom has moved 1 unit, correspondingly the second degree of freedom has also moved 1 unit. Okay. So, instead of having a curvilinear shape, this is being approximated using this shape. Okay. And this agrees with our intuitive solution that the system will behave in a saucer shape, and since there are no masses in between, this will be the mode shape. Okay. So, this agrees with our intuitive judgment. Okay. Now, we looked into the second frequency. Okay. So, the second frequency has a value, okay, and again we evaluate the value of R2, okay, depending upon the equation that we have. So, in the second mode, okay, if the first mode moves 1 unit positive, then the second mode will be moving 1 unit negative. It simply means that if these are the two masses, okay, if we are moving this 1 unit positive, the other one is going to move 1 unit towards the negative. Okay. Now, again we will visualize this thing using our beam analogy. So, in the beam analogy, okay, this was the second mode. Okay. So, this is the behavior that we are expecting in the second mode. Okay. And here, okay, in beam, this were our 2 degrees of freedom. So, the choice of 2 degrees of freedom was like this. So, here if this unit is moving 1 unit downward, the other one is going to move 1 unit upward. Okay. So, we can draw like this, okay, and we have to obey the boundary condition. So, the displacement at the two boundary conditions are 0. Okay. So, this is mimicking our second mode shape. Okay. So, this is the second mode shape. Okay. So, this again agrees to what we have seen earlier. Okay. If we have put more degrees of freedom, then the third one should look something like this. So, it means that the R matrix will look something like this, 1 minus 1 1, which will corresponds to my 3 degrees of freedom, 1 positive out here, 1 positive out here, 1 positive for this one, 1 positive for this one, and 1 negative for this one. Okay. So, it will look something like this. Okay. So, this will be our third mode, okay, and so on and so forth. Okay. So, our mode shapes, okay, are confirming our assumptions. Okay. So, the way we assumed our first mode, second mode, and if we have done the earlier mode, the higher modes also, then the mode shapes are conforming to the assumptions of those mode shapes. Okay. So, this little ways. Okay. So, using this type of earlier known systems, okay, we can cross check and verify our solutions also. Okay. Moving ahead, now we are again looking into the equations, okay, to the solutions of the equations. Okay. So, substituting value of the R1 and R2 into the equation. Okay. We know the values of R1 and R2. So, for first one, the value of R1 is 1 okay, and for the second case the value of R2 is 2. Okay. So, we get the solution for our x1 and x2. Okay. So, using this solution and applying the initial condition, we can calculate the value of A1 and A2. Okay. So, we calculate the value of our A1 and A2 by putting the values of R1, R2 and the initial conditions. Okay. So, initial conditions, we have assumed a disturbance at the first degree of freedom, initial displacement at the degree of freedom. Since this is a free vibration system, so there will be no forcing function and the motion will be due to an initial disturbance, okay, which is mimicked here by the displacement at the first motion. Okay. So, we are using this and putting back into the equation, we are trying to calculate the values of A1 and A2. Okay. So, for x1 we have this equation, for x2 we have this equations. Okay. So, if we do the calculations and put the values of the initial conditions, we will get the values of A1, A2. Okay. So, after doing the entire calculation set, okay, we got the value of A1 and A2. Okay. So, that this entire exercise you can practice and see if you come up with the same solutions. Okay. So, the entire thing has been given as a practice exercise. Okay. Okay. So, substituting the value of omega and omega 2 we have already calculated, A1, A2 we calculated, and the value of phi, we get the final equation of x1 and x2. Okay. So, this is the omega part, okay, omega 1 part, omega 2 part. We know the displacement at any given degrees of freedom will be a combination of the two modes. Okay. So, this contribution is coming from the first mode and this contribution is coming from the second mode, first mode and second mode. Okay. So, simply if we look back and try to change it into our analogy of the summation of Qn and phi n. Okay. So, the phi n part we approximated using a sine function. Okay. So, this becomes half, this entire thing becomes phi 1 plus half, the entire thing becomes phi 2. Okay. So, this entire thing we can write down as phi 1 and this entire thing is my phi 2. Okay. And phi 1 and phi 2, so it is a sine approximation. So, omega 1 was the first mode shape and omega 2 was the second mode shape. Okay. And the value of q1 and q2, okay, the value of is given by half. Okay. Similarly, for the second mode, again summation of phi 1 and phi 2, okay, and the value of the respective phis. Okay. So, at each degree of freedom there is a contribution from the first mode, there is a contribution from the first mode which is multiplied by an amplitude factor. Okay. So, this also establishes our assumption. Okay. We started the solution as summation of Qn and phi n from the individual modes. Okay. Phi was giving me the contribution from the mode shape. So, here it will be contribution from the two modes. So, this is the contribution phi 1 from the first mode, this is the contribution from the second mode phi 2 and this is the amplitude contribution Q1 and Q2. Okay. Similarly, for the other degree of freedom, this is my solution. Okay. And the same thing has been arranged in the matrix form. Okay. So, in this particular example, what we were able to establish is that we started with a simple 2 degree of freedom system, okay, that has only horizontal motion, okay, and the 2 degrees of freedom were due to the two masses, each mass was able to move independently, okay, in the horizontal direction. Okay. After that, we drew the free body diagram of the system. Okay. We draw the free body diagram of the system, and from the free body diagram of the system, we wrote down the equation of motion. So, from the free body diagram of the system, we wrote down the equation of motion of the system. Okay. We rearranged it. Okay. Now, these are the coupled equation. Coupled equation means that x1 and x2 are appearing together in each of the equations. Okay. After that, we wrote down the equation in the matrix form. Okay. So, these are the equation of motion for free vibration of an undamped system. Undamped system, forcing function is 0, free vibration means the damping term is 0. Okay. Then we assumed the solution. Okay. So, since this was a case of a free vibration system, so the solution has to be harmonic, as we have seen earlier for the single degree of freedom system also. Okay. So, we assumed a harmonic solution, okay, with Q1 and Phi1, okay, corresponding to the contribution from the individual modes and multiplied by an amplitude factor. Okay. Then we substituted this solution back into our equation of motion. Okay. And once we substitute this back, then A1 and A2 are non-zero. This matrix has to be non-zero for non-trivial solution. Okay. So, it means the determinant of this matrix should be 0, the determinant of this Q matrix has to be 0. We put this thing, and after that we calculated the value of omega. Okay. We wrote down this thing as a quadratic equation in omega square. We substituted omega 4 as omega square, and we wrote down this thing as a quadratic equation in omega square. Okay. So, we got the solution. Okay. From the solution we substituted back omega square out here, okay, and then we wrote down the values of the 2 omegas. Okay. So, using this thing we calculated the value of the 2 frequencies. Okay. So, right now we have 2 frequencies, we know the frequencies at which these 2 systems are going to oscillate. Okay. So, after that we wrote down the amplitude as a ratio. So, A2 over A1 we wrote down as the amplitude ratio. Okay. From the amplitude ratio, okay, we replace this thing using the amplitude ratio. Okay. And from the amplitude ratio we again wrote down the equation, and we calculated the amplitude ratios R1 and R2. Okay. Now, again recapping, the total response of the system is a summation of all the modes, okay, of all the modes multiplied by a amplitude factor. So, we have chosen 2 degrees of freedom. So, for each degree of freedom, okay, we will get the response contribution from all the modes. Okay. Since we are restricting it to 2 degrees of freedom, so we will only have contribution from the 2 modes. So, the value of x1, okay, will be a contribution from Q1 Phi1 plus Q2 Phi2. Okay. So, this will be the my general form of the solution. Okay. So, the same thing we are writing out here. Okay. After that we apply, what we need to do is that we need to apply the initial condition and calculate our A1, A2 and the phase lag portion. Okay. Because we have already calculated the frequencies, so only thing we need is the phase lag portion and the values of A1 and A2. Okay. So, after that we did one example, we assumed all the values of k. So, this is an example. Okay. So, in this example we assumed all k's are equal and all m are equal, okay, and we have an initial disturbance, okay, that is an initial displacement at this point. Okay. So, this is the initial condition, okay, and we are again assuming x1 is greater than x2. Okay. So, for this particular problem we calculated the 2 frequencies using the equations that we have already developed. Okay. So, we now know the frequency of first degree of freedom and the frequency of the first mode and frequency of the second mode. So, this one will be the first mode frequency and this is the frequency of the second mode. It means that this is the frequency of the first mode if we are using a beam analogy, and this is the frequency of the second mode. Okay. So, we have the 2 frequencies. Okay. After that we calculated the mode shape. Okay. For calculating the mode shape we use the ratios, the amplitude ratios. So, amplitude ratios are coming 1 and 1. It means that if we take the beam analogy, if this chosen degree of freedom moves 1 unit, the other one is also going to move 1 unit. Okay. It means that it will do this shape. Okay. Since there are no masses in between, okay, we model this thing as a lumped mass and the boundary condition has to be obeyed. Okay. So, 1 unit positive. So, this is the mode shape which corresponds to our earlier mode shape. Okay. We assume that the first mode is going to do like this, okay, in a sine form, and this is also mimicking the sine form. Okay. So, this agrees with our mode shape. Okay. Again we calculate the second mode is 1 minus 1. It means that 1 degree of freedom will move in one direction, the other one is going to move in the opposite direction. Okay. So, our mode shape is going to look like this, the boundary conditions are obeyed, and since no mass are in between, okay, this is represented like this. So, it obeys my second mode approximation. Okay. If there would have been other modes, okay, so let us say third mode, then the R would have been like this, 1 minus 1 1. So, it would have shown the third mode also like this. Okay. So, let us say this example had 3 modes. Okay. So, what would have been the values of R1? Okay. So, R would have looked, okay. So, for the first mode it would have been 1 1 1, okay, mimicking this shape. Second one would have been 1 0 minus 1, third mode would have been 1 minus 1 1. Okay. So, this is how R would have looked like if you would have assumed the 3 mode approximation. So, what can you do is that you can take the 3 mode approximation also, formulate this entire problem as a 3 mode system, okay, and see what are the values. Okay. So, as an example, what can be done is that you can write down as a 3 degree of freedom problem. Okay. So, this 3 degree of freedom problem can be formulated like this. Okay. Okay. All masses can be assumed m, m and m, 3 degrees of freedom, x1, x2, x3, and all could be assumed k, k, k. Okay. So, this way we can do a 3 degree of freedom system also, okay, just to see how it works out. Okay. After that we put the values of A1 and R1 into our equations of x1 and x2. Okay. After that we put the initial conditions. Okay. So, using the initial conditions we calculate the value of A1 and A2. Okay. So, we have the values of A1 and A2. You can use these things, okay, cross check and cross verify the value of A1 and A2. Okay. Similarly, we put the initial condition of the velocity. We have assumed that the velocity at time t equals to 0 at both the ends. Okay. So, we get the values of the unknown quantities. We got the values of the A1, A2 and the values of the phase lag. Okay. So, we have omega 1, omega 2 evaluated, A1, A2 evaluated and the phase lag evaluated. Okay. So, now we know that my total displacement will come from the summations of the contribution from the 2 modes. So, this is the contribution from the first mode, this is the effect of the second mode, and this is the amplitude contribution, okay, from the 2 modes. Similarly, first mode and the second mode. Okay. So, look here phi 1 and phi 2 remains. So, for each of them phi 1 and phi 2 is the solution. So, for each degree of freedom there is a contribution from the first mode, there is a contribution from the second mode. So, this is for y1. For y2 also there will be contribution from the first mode, there will be contribution from the second mode. Only thing is that the value of q1 and q2 will be different. Okay. So, we got the total solution of the system, and here the total solution has been written in the matrix form. Okay. Using trigonometric approximation, the same thing can be expressed and written in terms of the cost function also. Okay. So, with this thing what we have done is that we have taken an example of a 2 degree of freedom system. We have evaluated the 2 degree of freedom system, we have evaluated the frequency, we evaluated the mode shapes, we checked the mode shapes with the conventional knowledge that we have, and it seems that it agrees with the conventional shape. what can be done is that we can extend this same problem as a 3 degree of freedom system and can check for the higher modes also, and subsequently we can increase the number of degrees of freedom and can check for more number of degrees of freedom. Okay. So, similarly the same procedure will be used to formulate a multi degree of freedom system also. So, after we check the frequencies, after we check the mode shapes, we took one example in which it was again a free vibration response. In the free vibration response there was no damping, and the initial condition was due to an initial disturbance at one chosen degree of freedom. After that we calculated the displacements at the 2 degrees of freedom, and as we have seen in the previous knowledge, the total contribution will be due to the contribution from each of the modes, and here also we got the same response. We got the summation of Qn phi n over the entire spectrum. We have chosen the 2 degrees. So, 2 mode shapes were there and the corresponding values of Q1 and Q2 were there. So, we have established the solution for this 2 degree of freedom system also. So, with this I stop here and I ask you to practice these problems, and if possible extend this thing into more number of degrees of freedom. Thank you.